Find the dimensions of a right circular cylinder of maximum volume that can be inscribed in a sphere of radius 3 inches. So let's start by sketching a graph of this. And while this is a right circular cylinder in a sphere, so it's in 3 dimensions, I'm going to do my sketch here in 2 dimensions to make it a little bit easier to visualize. So here is our sphere. We know that it has a radius of 3. And then within this sphere, we have a right circular cylinder. So in 2 dimensions, this will look like a rectangle. So we'll keep in mind this is the center point of both that cylinder and the sphere. So we can say from that center point to any point on the circle is that radius of 3. We can say that this, from top to bottom of the cylinder, is the height of the cylinder. And then from the top, middle, all the way to that adjacent point is the radius of our cylinder. And so we want to find the dimensions of that right circular cylinder. So we know that the volume of a cylinder is defined as pi r squared times the height. So in order to maximize the volume of this cylinder, we need to rewrite it in terms of one variable. So here's where our graph is going to be particularly useful. And we can already see it taking place here. What we've done by sketching this in 2 dimensions is that we've identified that these 2 equations are related by a right triangle. So we can define this extra side here as half of the height of our cylinder. So we know that by Pythagorean's theorem, that the sum of the square of the 2 shorter sides is equal to the square of the longer side. So we can say that our radius squared plus the height divided by 2 squared is equal to 3 squared. And simplifying, I have r squared plus the height squared by 4 is equal to 9. And then looking back at the equation that we're trying to maximize, our objective equation, we see that it contains an r squared, which is also contained in Pythagorean's theorem. So we can solve here for r squared and say that our radius squared is equal to 9 minus the height squared divided by 4. And so we have established a constraint equation that we can now go ahead and substitute into the objective equation. And this will allow us to apply our first derivative test. So we are going to rewrite the volume. So we are again taking that volume, which was pi times the radius squared times the height, and we can now say that this is equivalent to pi multiplied by 9 minus the height squared over 4 multiplied by the height. And to simplify, we'll distribute our h through to both terms, which leaves us with pi multiplied by 9h minus h cubed, all divided by 4. And we're now ready to go ahead and find the critical points. So differentiating first, we have the derivative of volume here is going to be equal to pi multiplied by 9 minus 3 times the height squared over 4. And we can now set this equal to 0 and solve for h. So setting this equal to 0, we can divide both sides of the equation by pi, which leaves us with 9 minus 3/4 times the height squared is equal to 0. So I have a minus 3/4 times the height squared is equal to negative 9. And multiplying both sides of the equation here by the reciprocal of our fraction, so multiplying both sides by negative 4/3, we are left here with our height squared is equal to, and we can actually simplify a little bit further on the right-hand side. We know that 3 goes into 9 3 times. We also have a negative multiplied by a negative, which becomes positive. So we have 12. We have h squared is equal to 12. And then last but not least, we can take the square root of both sides, which leaves us with height being equal to plus or minus. We think about the perfect squares that live within the factors of 12. So we can simplify this to plus or minus 2 multiplied by the square root of 3. So again, we have two distinct solutions here. We have the height could be 2 times the square root of 3, or that our height could be equal to minus 2 times the square root of 3. But we know that we cannot have negative dimensions, so we can disregard our negative solution here. So therefore our height, and we should include this, is a height of 2 times the square root of 3 inches. And so this value will yield a maximum volume for the cylinder. So we also, in addition, again, the question asks us to find the dimensions and the volume. So we want to use this to find the maximum, or the dimension, for the radius that maximizes volume. And to do this, we can think back from Pythagorean's theorem that we know that our radius squared was equal to 9 minus the height squared all over 4. So we have 9 minus 2 times the square root of 3 squared over 4. So we have 9 minus 4 multiplied by 3 divided by 4. We can simplify. Those 4's cancel each other right out. So we're left with a radius squared of 9 minus 3, or 6. And so we're left with a radius being equal to plus or minus the square root of 6. Again, we cannot have negative dimensions. So therefore, the radius that maximizes the volume is just the square root of 6. And don't forget inches. So these are the dimensions that maximize the volume, and we'll now use them to find the maximum volume. So the volume of a cylinder is pi r squared times the height. So this is going to be pi multiplied. So actually, if we look back up here, we already know that the radius squared is 6. So that's going to be pi multiplied by 6. Oh, shame on me, forgot this would be inches squared, multiplied by the height, which is 2 times the square root of 3 inches. And so therefore the maximum volume is 12 times the square root of 3, and this is inches cubed. And this is our beautiful final answer.